चोपड़े, ऋत्विक गुणे, सदाशिव, सागर, साई प्रकाश,
Present, sir.
राइट, समीर अहमद, सानिया,
Present, sir.
ओके, संजय, संकल्प, संकेत,
Yes, sir.
राइट, शिरज,
Present, sir.
राइट, शिवनंदा नाटिकर, श्रद्धा,
Present, sir.
राइट, शुभम,
Present, sir.
ओके, सुमित, सुरैया बानु,
Present, sir.
राइट, तेजस, विवेक, यमुनप्पा, गांवकर रजत रामचंद्र, मंजुनाथ, प्रथमेश, जोसलिनो, सोहम, अतिया. Anybody joined?
Sir,
I have marked yours. Anybody else? Okay. Today let us solve the assignment questions, right? The first assignment question, that is, explain the hybrid model and develop the hybrid model for the common emitter, common base and common collector configurations. Okay, first question, explain the hybrid equivalent model and develop the hybrid equivalent model H model for the common emitter, common base and common collector configurations. What is a hybrid equivalent model? Consider the two-port network. This is a two-port network. II and IVI are input current and input voltage. I0 and V0 are output current and output voltage. Now, if you want to develop the hybrid equivalent model, then we have to assume two variables as independent variables and two variables as dependent variables. Here we are assuming II and V0 as independent variables, II and V0 as independent variables, whereas I0 and Vi as dependent variables. Then the dependent variables are expressed in terms of the independent variables. That is, Vi is a function of II and V0. I0 is a function of II and V0. Okay. Are you able to see the screen here? Screen is visible?
Yes, sir.
Okay. Then next is we are writing the function in the form of equation, that is Vi is equal to H11II plus H12 V0 and I0 is equal to H21II plus H22 V0. Okay, in terms of H11, H12, H21 and H22. Now these H11, H12, H21 and H22, they are called H parameters or hybrid parameters. They are called as hybrid parameters because the units of these parameters are not same, and hence they are called as hybrid parameters or the H parameters. Now, if you want to define these hybrid parameters, if you want to get the equations for these H parameters, then we have to short circuit the V0 equal to 0. That is, we have to make this V0 equal to 0, independent variable V0 equal to 0. That is, short circuit the output terminals. If we short circuit output terminals, then equation 3, in equation 3 V0, if we put 0, then what we'll get, II will be equal to, that is H11 will be equal to Vi by II. H11 will be equal to Vi by II at V0 equal to 0, where H11 is called input impedance with output short circuited and its unit is ohms. Similarly, if we put V0 equal to 0 in equation 4, this equation, then we get H21 is equal to I naught upon II. So this is the ratio of the currents, and hence it is called as short circuit forward transfer current ratio I naught by II, and it also has, and it doesn't have any units. It doesn't have any units. Next condition is we are substituting the one more independent variable II is equal to 0 next time. If we put II is equal to 0 in equation 3, then we get H12 is equal to Vi by V naught. H12 will be equal to Vi by V naught at II is equal to 0. This H12 is called open circuit. It is a ratio of voltages, open circuit reverse transfer voltage ratio, and it also has no units. It also has no units. Then similarly, if we put II is equal to 0, II is equal to 0 in equation 4, then we get H22 is equal to I naught upon V naught. H22 is equal to I naught upon V naught. This is the ratio of current to voltage. It is the inverse of the resistance, and hence it is called as admittance. It is the admittance. H22 is open circuit output admittance and has the unit mho. Mho is the unit of the admittance. Now using these H11, H12, H21 and H22, which are the hybrid parameters, then I is represented as 1, 1. It is the input parameter, hence it is 1, 1. O represents the output parameter, it is 2, 2. Okay. Here H11 is input impedance, it is 1. Then H21, it is represented as I. H21, it is forward transfer current ratio, it is represented as F. Okay. Then H12, it is reverse transfer voltage ratio, it is represented as R. Then H22 is output admittance, it is represented as O. Using these, we are writing the equation. We are replacing H11, H12, H21 and H22, and we write it as Vi is equal to Hi II plus HR V naught, and I naught is equal to HF II plus H naught V naught. Now what is this equation? Vi is equal to Hi II plus HR V naught. It is the KVL equation. It is KVL equation. And second equation, I naught is equal to HF II plus H naught V naught, is the KCL equation. It is the KCL equation. Now this KVL and KCL equation is done in the form of a model. It is like this: Vi is equal to Hi II plus HR V naught. HR V naught is dependent on Vi, and hence it is the controlled voltage source. It is a controlled voltage source. Similarly, the second equation, KCL equation, is I naught is equal to HFII plus H naught V naught. It is HFII which is dependent on I naught, and hence HFII is a controlled current source. Okay, so we developed the hybrid equivalent model. In general, the hybrid equivalent model will be combination of these two. That is this KVL equation and KCL equation. Combination of these two, we will develop the hybrid equivalent model in general for any circuit. That is, this is how we are combining the previous two and obtaining the hybrid equivalent model. Now, once we have developed the hybrid equivalent model, then next is, so for common emitter, common base and common collector, HI will be HIE, right? HF will be HFE, like this for each of these configurations. Then coming to the hybrid model of common base configuration, the fundamental equations are Vi is H11 II plus H12 V naught. I naught is equal to H21 II plus H22 V naught. This Vi is for the common base configuration. Here base is common, right? Then input is applied to emitter terminal. It is input current is IE. Output is taken from the collector terminal. Output current is IC. Input voltage is VEB. Input current is IE. Output current is IC, and output voltage is VCB. Okay. Now using this, we will substitute here Vi, I naught, II, and V naught. Then H11, as it is for the common base, it is H11 means it is HI, but for common base it will be HIB. Similarly, H12 is HR. For common base it will be HRB. Similarly, we have IC is equal to HFB IE plus HOB VCB. Based on these equations, the hybrid model of the common base configuration is developed. That is, first equation is the KVL equation, second one is the KCL equation. This is the KVL equation. VEB is equal to HIB IE plus HRB VCB. And KCL equation is IC is equal to HFB IE plus HOB VCB. This is the hybrid model of common base configuration. Then second one, for common emitter configuration, again take the same two equations. Vi is equal to H11 I1 plus H12 V naught. I naught is equal to H21 II plus H22 V naught. Now these equations will become, For VI, for common emitter configuration, how is the common emitter configuration? In common emitter configuration, emitter is common between input and output portions. Input is applied to base, output is taken from the collector. Input current is IB, then input voltage is VBE, output current is IC, then output voltage is VCE. Substituting these equations, fundamental equations, we get VBE is equal to H11 is HI, but for common emitter it will be HIE, H12 is HR, for common emitter it is HRE, then H21 is HF, for common emitter it is HFE. Like that we get IC is equal to HFE IB plus HOE VCE. Again, based on these two equations, that is first one is KVL, second one is KCL, the hybrid model of the common emitter configuration is drawn. Excuse me. Then coming to the hybrid model of common collector configuration, Vi is equal to H11 I1, same equations plus H12 V0. I0 is equal to H21 II plus H22 V0. Now these equations will become, if it is a common collector, then input is applied to base, output is taken from the emitter. The input current is IB, input voltage is VBC, output current is IE, and output voltage is VEC. Based on these equations, the hybrid model for the common collector is done. That is, considering the equations, VBC is equal to HIC IB plus HRC VEC, IE is equal to HFC IB plus HOC VEC. Then we get the hybrid model of the common collector configuration. So this is the hybrid model of the common collector configuration. Okay, this is the first question. Okay, so when it is asked this question, see the marks and then write the answers. Your answer should always be based on the marks. Judge for this much marks how much I have to write. If it is asked for more marks, you have to expand your answers. If it is asked for less marks, you have to shorten your answers. You have to reduce your answers, right? The next question is, derive the expression for Zi Z0. Excuse me. Derive expression for Zi Z0 and AB of fixed bias circuit using RE model. This is the common emitter fixed bias configuration. The question is, derive expression for Zi Z0 AV voltage gain of fixed bias circuit using RE model. RE model is the AC model, AC equivalent model is the RE model. So in the common emitter fixed bias configuration, we have the base resistance, collector resistance, emitter terminal is grounded. There is no emitter resistance present here in the fixed bias configuration. Then input voltage Vi, output voltage V0, VCC, right? Then Zi and Z0, VBE, VCE. Okay. So in this fixed bias configuration, we are converting it into AC equivalent circuit. If you want to develop the AC equivalent circuit, we know that the capacitors will become the short circuit. Capacitors are short circuit here, C1 and C2. Then DC voltage will become 0, VCC will be 0. RB will be connected between base to ground. RB will be connected between base to ground. Then RC will be connected between collector to ground. RC will be connected between collector terminal to ground because VCC is 0. Therefore, RC is connected between collector to ground. Then we have emitter terminal to ground. Now this circuit I am drawing it in the form of the equivalent circuit. That is, Vi is there, RB is in between base to ground, RB is in between base to ground. Then we have the transistor. Then at the output side, we are having RC connected between collector to ground. RC connected between collector to ground. Again, this is converted into RE model. Next is RE model. Input side it is RB connected between base terminal to ground. RB is connected between base terminal to ground. Then we have base to emitter, that is nothing but AC resistance, small re, that will be converted into beta re. That will be converted into beta re for common emitter configuration. Therefore, here we will get beta re, right? Then on the output side, The collector current is IC is equal to beta IB. That is, here you will get beta IB. It is flowing into the circuit, right? Because it's a two-port network, according to the convention, it flows into the collector terminal, into the circuit, output current. Then R0 is there, output resistance R0. Output resistance are not present here. That is also considered. Input resistance is not considered, Ri, because it is negligibly less, it is neglected. But output resistance is present, output resistance is more, and hence it is shown here. Then the collector resistance RC is connected between collector to ground. Yes or no? RC is present between collector to ground. Then we write the input current is II, ZI input impedance, IB current into the base terminal. Then I0 is the output current, IC is the current flowing into the collector terminal. Z0 we have. What is ZI? ZI is VI by II. Input voltage by input current is ZI. Then we know that Zi, from if you look into this circuit, Zi will be the parallel combination of RB and beta RE. That is RB parallel beta RE. Zi is equal to RB parallel beta
Sir.
RE. Yes.
Sir, hello, Samir sir.
Okay, 1 minute. Yes, I have admitted him. Thank you. Then Zi will be RB parallel beta RE. RB parallel beta RE here. Okay. It is Zi. Next is, if we want to find the output impedance, what is the rule? We have to make the active sources 0. Yesterday only we have seen for the Darlington emitter follower, we are making the input voltage 0. Similarly, here make the input voltage Vi equal to 0 if you want to find the output impedance. Now, if we make Vi equal to 0 here in this RE model, current II will be 0, IB will also be 0. If IB is 0, then beta IB will be 0. If beta IB is 0, then the circuit will be, this will be open circuit, beta IB, then we have only R0 and RC present in the collector side. Circuit will be like this. This is open circuit, beta IB, then we have only R0 and RC. Therefore, Z0 will be parallel combination of R0 and RC. Z0 is equal to R0 parallel RC. Next, let us find voltage gain. To find voltage gain, consider again the output equivalent circuit. Beta IB R0 RC, only the output side. Beta IB R0 RC, right? This is nothing but beta IB. R0 parallel RC is Z0. I am writing it as Z0. R0 parallel RC. It is represented as Z0. Now we have to find the voltage gain AV. The equation voltage gain is V0 by Vi. Let us find V0 first. V0 is equal to minus beta IB into Z0. Okay, if we want to find V0 here, it is minus beta IB into Z0. Okay, this will be current entering positive, current leaving negative. Okay, so it is here, as it is moving into the terminal here, into the terminal, right, into the ground side. So this will be V0 is equal to minus beta IB. Okay, V0 is equal to minus beta IB. That is the equation for the output voltage, because the current direction is towards the ground terminal, right? Therefore V0 will be equal to minus beta IB. Minus beta IB into the resistance, that is Z0, minus beta IB into Z0. This V0 will be equal to minus beta IB. Z0 is R0 parallel RC. Just substitute that R0 parallel RC. R0 parallel RC. Now from the input circuit, this is the output side. Let us consider the input section now. Input section is AC current circuit with the RE model. So we get the value of VI. So VI will be equal to, this is across, therefore VI will be equal to IB into beta RE. It is in parallel. VI will be equal to the current multiplied by the resistance IB into beta RE. Vi will be equal to IB into beta RE. Vi is IB into beta RE. Now voltage gain is V naught by Vi. Substitute this equation, V naught minus beta IB into R naught parallel RC. That divided by Vi is IB into beta RE. Then IB beta cancels. We will get minus R naught parallel RC by RE. If RB is greater than 10 times beta RE, here we have to consider two conditions. First condition is if RB is greater than or equal to 10 times beta RE, then RB parallel beta RE. If RB is equal to say 10 times beta RE, that is base resistance, then 10 times beta RE parallel with beta RE. Parallel combination of large value with smaller value will be smaller value only. Therefore, 10 times beta RE parallel beta RE will get only beta RE. Therefore, the equation 2 becomes the equation 2. Equation 2 is RB parallel beta RE. So this will become only beta RE. This will become only beta because it is RB parallel beta RE. 10 times beta RE parallel with beta RE, that will be beta RE. Similarly, for the output, we have to consider the condition R naught greater than or equal to 10 times RC. For input, the condition is RB greater than or equal to 10 times beta RE. And for the output side, the condition is R naught if it is greater than or equal to 10 times RC, because output resistance R naught is present. Now, R naught equal to 10 times RC, that is RC parallel 10 times RC. Parallel combination of large value with small value will be small value only. Therefore, we'll get only RC. Right? Now, Z naught is approximately equal to Z naught equation 3. Z naught is R naught parallel RC. 10 times RC parallel RC will be RC only. Therefore, we'll get Z naught equal to RC. Then AB equation is minus R naught parallel RC divided by RE. Minus R naught parallel RC will be RC only. Therefore, minus RC by RE. Minus RC by RE. AV equation, gain equation. Next is current gain. AI is I naught upon II. Ratio of output current to input current. V naught is, what is the equation for V naught from the RE model? Whatever performance parameters we are deriving, they are all derived from the RE model only. Whichever may be the circuit here in AC analysis module 2, we are deriving the performance parameters by considering the RE model. What is the equation for current gain? I naught by II. Now, what is I naught and what is II? We have to find out. V naught is equal to, from the RE model, here V naught is equal to output current into output resistance. That is V naught is equal to I naught into RC. V naught is equal to I naught into RC. Right? Here current entering positive, current leaving negative. Okay. So it is minus positive to negative minus I naught RC. Then output side voltage terminal positive negative minus V naught is equal to 0 or V naught is equal to minus I naught RC. Current entering positive, current leaving negative, minus I naught RC positive to negative, minus V naught equal to 0 or V naught is equal to minus I naught into RC. Therefore, we have V naught is equal to minus I naught into RC, or I naught is equal to minus V naught by RC. Similarly, write the equation for the input current II. II is input voltage by input impedance. That is II is equal to Vi upon Zi. Vi by Zi, that is input current II. Now we got I naught and II. Substitute in the equation for the current gain. Substitute in the equation for the current gain. Then using these relations, AI is equal to minus V naught by RC, that is I naught. This divided by II. II is Vi by Zi. This will be minus V naught by RC into Zi upon Vi. That is minus V naught by Vi into Zi by RC, or AI is equal to V naught by Vi is voltage gain minus AV into Zi divided by RC. Now using these equations 9 and 7 for AV and Zi, we obtain. Let us consider equation 9 and 7 for AV and Zi. We are substituting for AV and Zi. Equation 9 is minus RC by RE. AV is minus RC by RE, whatever we have derived. Then equation 7 is Zi is beta RE. Substitute this here in the final equation. We get AI is equal to minus 1 by RC. Then AV is minus RC by RE, minus RC by RE. Then Zi is beta RE. Substitute them, then we will get AI is approximately equal to beta. So we have derived the equation for input impedance, output impedance, voltage gain and current gain. These are the performance parameters of the fixed bias circuit. Okay. Then negative sign in the equation of AV voltage gain, it indicates that the output voltage and the input voltage are 180° out of phase, because AV is minus R naught parallel RC by RE. Negative it is. Okay. Next question, question number 3. Question number 3. This is a problem that is asked in the question 3 of the assignment. For the emitter follower shown below, calculate RE, ZI and Z0, AV and AI. Take beta equal to 100 and R0 equal to infinity. This is the emitter follower circuit. We have base resistance. There is no collector resistance, and there is emitter resistance. Output is taken from the emitter. Output is taken from emitter. Input is applied to base terminal. The output at emitter follows the input at the base. Hence, it is called as emitter follower circuit. So for this circuit, they have given beta value and R naught as infinity. You have to find first one AC resistance RE, input impedance ZI, output impedance Z0, voltage gain AV, current gain AI. Okay, considering beta equal to 100 and R naught equal to infinity. We know the equation for the IB of emitter follower circuit. What is the equation for IB for the emitter follower circuit? It is VCC minus VBE. We know how we are finding the IB equation, right? We are applying the KVL to the input path, input portion. So if you all go on finding the equations by applying the KVL to the input side and output side, it will take more time. Time will not be sufficient. So better you all memorize these formulas, right? Now, these formulas, these performance parameters, what all are there, or the DC equations, DC analysis equations, what all are there in module 1, right? Write them in your notebook or write them in a page, right? And you can stick it onto your study table wherever you are sitting for study. You can stick it there, right? And then whenever you go to your study table, you can see those equations and memorize them. Repeatedly memorize them. Okay, memorize the equations. What are the performance parameters of the fixed bias configuration? What are the performance parameters of emitter follower circuit? What are the performance parameters AV, AI, ZI and Z0 for voltage divider bias? What are the performance parameters for collector to base bias? Right, like this. What are the performance parameters for all the circuits? Write them down, right? The equations, various equations, and you can write it down in your notebook and repeatedly memorize them. Repeatedly memorize them so that you'll be able to remember the formulas. So this is how you all have to study. And when studying, I told you all that you have to compare how is this circuit different from the previous circuit. Now just I give the example of emitter follower and the Darlington emitter follower. They are almost same. The RE model is also same. There is slight difference. Okay, so like this, whenever you are studying, you have to compare the circuit with the previous circuit that you have studied, or what all circuit you have studied in your previous classes, and then accordingly you have to memorize the formulas. Okay, and remember the circuits and the various equations. Okay, so do like this, it will be easier for you to remember the formulas. Now, equation for IB for the emitter follower circuit is VCC minus VBE divided by RB plus 1 plus beta into RE. VCC minus VBE divided by RB plus 1 plus beta into RE. Okay. That is 12 minus VCC is given 12 minus 0.7 divided by VB is 0.07. Sorry, 0.7. This divided by RB. RB base resistance is 220 kilo ohms plus 1 plus beta. Beta is 100 into RE. RE is 3 point emitter resistance. This will be 20.42 microampere. Then IE is 1 plus beta into IB, that is 1 plus 100 into IB. What just now we got 20.42 microampere. This will be 2.062 milliampere. Next, if you want to find the value of RE, it is we know that RE is 26 millivolt by IE. The standard equation for RE is 26 millivolt by IE. Substitute IE, we get 12.61 ohms. So we found out AC resistance Re. Next is Zi. Now if you want to find Zi, let's first we have to find out ZB. ZB is beta Re plus 1 plus beta into Re, the main equation. ZB is beta into Re plus 1 plus beta into capital Re. Okay, it is 100 into small r is 12.61 plus 1 plus 100 capital Re emitter resistance 3.3 K. This will be 334.56 kilo ohms. Then Zi, it is Rb parallel Zb. Rb parallel Zb, that is 220 kilo ohm. 220 kilo ohm is Rb parallel with Zb, that is 334.56 K. This will be 132.72 kilo ohms. And similarly, Z0 will be Re parallel Re, that is capital Re parallel small re, that is Z0 in the emitter follower, that is 3.3 K parallel with 12.61 ohms. This will be 12.56 ohms. Next is voltage gain, that is Re divided by Re plus Re. Voltage gain formula for emitter follower is capital Re divided by capital Re plus small re. That is 3.3 K divided by 3.3 K plus 12.61 ohms. This comes out to 0.996. Then current gain formula is AI is equal to minus AV into ZI divided by capital Re. That is, so remember, wherever it is capital R, you have to make use of capital R. Wherever it is small r, you have to make use of small r. Right? If you are using this capital R in place of small r, or if you are using small r in case of in the place of capital R, then you will go wrong. Okay? You have to remember wherever it is capital R, wherever it is small r, just remember them clearly and then use them in the equations. So AI is minus AB into Z divided by capital RE, that is minus 0.996 into 132.72 K divided by 3.3 K, that comes out to minus 40. Okay, we have derived the performance parameters, that is RE, ZI, Z0, AV and AI. Okay, these are the performance parameters for the emitter follower circuit. Okay. Next one is the emitter follower circuit using collector resistor. Okay, question number 4. Question number 4. Let me take up that. This is the example that is asked in question number 4. For the circuit shown below, calculate RE, ZI and Z0, AV and AI. Consider beta equal to 100 and R0 equal to 50 kilo ohms. Okay, which circuit is this? Can anybody identify? Emitter follower using collector resistor. Note that it is not voltage divider bias. I told you all the difference between voltage divider bias and emitter follower using collector resistor. Okay, so in voltage divider bias, the output is taken from the collector terminal, whereas in emitter follower circuit using collector resistance or collector resistor, output is taken from the emitter terminal. Okay, so in this emitter follower circuit using collector resistor, these are the given values. Beta is given, R not equal to 50 kilo ohms. This is one way of asking. I told you all another way of asking. So they may ask in the form of a statement. For the emitter follower circuit using collector resistor, the values given are R1 equal to 100K, R2 equal to 15K, RC equal to 4K, RE equal to 1.2K, beta equal to 100 and R not equal to 50 kilo ohms. Find the values of RE, ZI, Z0, AV and AI. They may ask in the form of a statement, or they may give you the circuit and they may ask. There are two ways of asking the same question. Okay, remember these two options, and accordingly you have to first write the given data, use the equations, required equations for that required circuit, and then start solving the problem. Okay. Here we are using exact analysis for the voltage divider bias. It is the same analysis that is applicable here also for the emitter follower circuit using collector resistor, because the circuit is same. Okay, only this RE resistance is coming. Okay, here this output is taken only from the emitter terminal, but the circuit, basic circuit remains the same as that of the voltage divider bias. Hence we are using the exact method of the voltage divider bias here. What is the approximate method of voltage divider bias? Or if we want to apply the approximate method for the voltage divider bias, then beta RE should be greater than 10 times R2, right? beta RE should be greater than 10 times R2 if we want to make use of approximate method of voltage divider bias analysis. There are two methods of DC analysis of voltage divider bias, that is exact analysis and approximate method. Okay, so if we want to make use of approximate method, then the condition is beta RE should be greater than 10 times R2. Now what is RE here? Beta into RE. Beta is 100, RE is 1.2. 100 into 1.2 K is 120 K. Okay, that is greater than 10 times R2. R2 is 15K. 10 into 15 is 150K. So beta into RE is not greater than 10 times R2. It is less. 120K is less than 150K. Therefore, we cannot make use of approximate method of analysis for this circuit. We use exact method. In the exact method, we are finding the R Thevenin and E Thevenin. Thevenin voltage and Thevenin resistance. Thevenin resistance is given by parallel combination of R1 and R2. R1 parallel R2, that is 100K parallel 15K. This will be 13.043 kilo ohms. Similarly, Thevenin voltage ETH. Thevenin voltage is the voltage that is present here at this junction. Okay, it is ETH is equal to VR2, that is ETH is equal to VR2, that is VCC according to voltage divider rule, VCC into R2 divided by R1 plus R2. VCC into R2 divided by R1 plus R2. VCC into R2 divided by R1 plus R2. That is Thevenin or V Thevenin. Substitute the values. VCC is given 18 into 15K divided by 100K plus 15K. This will be 2.3478 volts. Now find the base current. Okay, we know how to find the base current. IB is equal to ETH minus VBE divided by RTH plus 1 plus beta into RE. IB is ETH minus ETH Thevenin voltage minus VBE divided by Thevenin resistance plus 1 plus beta into RE. Okay, input side. Substitute the values, we will get 12.2747 microampere. Then I is 1 plus beta into IB, that is 1 plus 100 into IB, that is 101 into IB. We have calculated 12.2747 microampere. Substitute, we will get 1.23 milliampere. Then find RE. RE is 26 millivolt by I, standard equation. 26 millivolt divided by 1.23 milliampere. That comes out to around, that is 21.130. Okay, let's check out that. 21.13, yes, 21.13 K. Okay, sorry, ohms, it is 21.13 ohms RE value, small RE. Then ZB, next one. If you want to find ZA, first we have to find ZB. ZB is beta into small re plus capital RE. Formula for ZB is beta into small re plus capital RE, that is 100 into 21.13 plus 1.2K. 21.13 small r just now we have calculated. Capital RE, it is available from the circuit. This emitter resistance, it is 1.2K. Substitute them, we will get 122.11K. Then ZI is RB parallel ZB, RB parallel ZB. Okay. Then RB is, first find RB, that is R1 parallel R2. R1 is 100K, R2 is 15K. RB will be R1 parallel R2, that is 13.04 kilo ohms. Therefore, substitute for ZI now. ZI is RB parallel ZB, that is 13.04 kilo ohms parallel with ZB, that is 122.11K. We'll get 11.78 kilo ohms. Similarly, Z0, that is output impedance, will be capital RE parallel small re. Output impedance Z0 will be capital RE parallel small re. It is 1.2K parallel with 21.13 ohms. This will be 20.76 ohms. Equation for voltage gain, capital RE divided by small re plus capital RE. It is 1.2K divided by 21.13 plus 1.2K, that will be 0.983. Next is the equation for current gain, that is minus AB into ZI divided by capital RE, that is minus 0.983 into 11.78K divided by 1.2K, that comes out to minus 9.65. Okay, so these are the various performance parameters, that is for the which circuit? Emitter follower using collector resistor. Emitter follower using collector resistor. Okay, we obtained the values of RE, AC resistance, input impedance ZI, output impedance Z0, voltage gain AV, and current gain AI. Okay, what are the formulas here? Formula for RE is 26 millivolt by IE, then IB is RTH is R1 parallel R2, ETH is VCC into R2 by R1 plus R2, IB is ETH minus VB divided by RTH plus 1 plus beta into RE, IE is 1 plus beta into IB, ZB is beta into small re plus capital RE, Zi is RB parallel ZB, then Z0 is capital RE parallel small re, voltage in EV equal to capital RE divided by small re plus capital RE, then current in EI will be minus EV into ZI divided by capital RE. Okay, so these are the various performance parameters. Okay, the next class I will be covering up some more assignment questions that we'll take up in the next class. I'll inform you all when I'll be taking the next class. The next class, let us cover up some more assignment questions. Okay, sorry. Any doubts here, students? Any doubts here? Was it understood, students? Students? So practice these examples. Okay, practice these examples. It requires practice. Memorize the formulas. Memorize the formulas as I told you all, the method, how you are allowed to memorize the formulas. Repeatedly see the formulas, memorize them, remember the formulas so that you'll be able to use the formulas and solve the numericals. Okay. Ankita? Ankita?
Yes, sir.
Was it understood, Ankita?
Yes, I understood.
Okay. Janvi? Prajwal Gowda?
Yes,
Okay. Prajwal Gowda?
sir.
Fine.
Yes,
Ratan?
sir.
Understood, Prajwal Gowda?
Yes, sir. Understood, sir.
Okay. Ratan? Ratan? Sai Prakash?
Yes, sir.
Was it clear, Sai Prakash?
Yes, sir. Clear, sir.
Okay. Sania? Sanket? Sanket? Shiraj? Shiraj?
Yes, sir.
Was it understood, Shiraj?
Yes, sir.
Fine. Shraddha?
Yes, sir.
Is it clear, Shraddha? Today's examples that we discussed, assignment questions. Any doubts in them?
All clear.
Okay,
Sir.
right.
No,
Okay,
sir.
fine. Okay, okay. Shubham? Shubham?
Yes, sir, understood.
Okay. Suraya Banu? Suraya Banu? Okay. Then we'll continue with the next questions. Okay. In the next class, I'll be covering up the other questions that we'll take up in the next class. Okay. Thank you.